Now, let's talk about the behavior and analysis of trusses. And let's start by thinking back to our beam. As we learned last week, beams take perpendicular forces and convert them into a bending stress profile that looks like this, with the most amount of tensile and compressive stress concentrated at top and bottom. So really, it's the flanges that are doing the majority of the work in a wide flange beam section. The top flange provides compressive resistance, and the bottom flange provides tensile resistance when we have a simply supported beam with a load applied vertically downward. Together, these resistive forces create a resistive moment. With a truss, it's also the top and bottom chord that are primarily providing resistance. The top chord provides compressive resistance, and the bottom chord provides tensile resistance. And together, those resistive forces create a resistive moment. But working backwards now, we did not get these forces in these chords through a bending stress profile. Instead, it's these diagonal pieces that are doing the work to convert these perpendicular forces into horizontal forces that the chords can resist. As we mentioned earlier, none of the elements of a truss are typically designed for bending, with the exception of the top chord, but more on that later. For now, let's think about how a truss resists a perpendicular force purely through axial internal forces. So if I apply a load down here at this node, what will happen? We know that the load cannot travel into the bottom chord here because the bottom chord is perpendicular to the applied force. And since we've pinned either end, the load in the chord must be aligned with its axis, so it must be horizontal. So the load cannot get into the bottom chord directly, but it can go into this diagonal member here. It can also go into this vertical piece. So a portion of the vertical force that we've applied will travel up this vertical piece, and a portion will be resisted by this diagonal piece. And as we saw with the arch demonstration, along with this vertical component to resist the vertical force, there will also be a horizontal component that is generated. And so the total force is aligned with the axis of this diagonal member. And as we reach the node on the other end of this diagonal member, it's this horizontal component that will be transferred into the top chord as a compressive force. And back at the other end, it's the horizontal component that will be transferred into the bottom chord as a tension force. And so, it's the top chord that goes into compression, the bottom chord that goes into tension, which generates our resistive moment to this perpendicular applied force. And it's the diagonals that we're able to convert the vertical force into horizontal forces for the top and bottom chord to resist. Without the diagonals, the truss would not perform as it should. And let's look at an example of what it would look like to remove those diagonals. So here I have a simply supported beam on top and a broken truss with no diagonal members on the bottom. Let's compare their behavior under the same loading conditions. We already know that the beam will provide resistance to the applied force through bending. And so its deflected shape will look something like that. And its moment diagram will look something roughly like this. But what about our broken truss at the bottom? we have all of these extra pieces here that we've added. So will we get any extra resistance to bending from these pieces? Well, based on our discussion so far, if you think about what will happen to this applied load here, this vertical piece underneath here cannot convert this vertical load that we've applied into a vertical and horizontal component. And so all it can do is pass the load down to the bottom here, where it meets the bottom chord, which is perpendicular. And since this joint here is pinned, that perpendicular force cannot travel into this bottom chord. And so this bottom chord will provide no resistance, meaning that the force will not travel down this vertical member, and instead all of the load will be resisted by this top chord. At least that's how it should work. Now let's see if our prediction is true. So if we look at the deflected shape, we see that the deflected shape of the top chord is equal to the deflected shape of the beam. And if I look at the values here, at this node we have 1.36 inches of deflection, and we have the same deflection at our broken truss down below. Similarly, with our moment diagram, if I turn that on, you can see we have the same exact moment diagram for our top chord of our broken truss as we did with our beam, with a maximum moment of 36 foot kips. And so this broken truss here, because it has no diagonal members, is essentially just a beam with some pieces dangling off of it. So trusses with pinned joints like this need diagonal members in order to work properly. Now let's hop back to our OneNote document. So our diagonal pieces convert vertical forces into horizontal components for the top and bottom chords to resist. And keep in mind that it's very important that we apply loads only at these panel points for this behavior to hold true. If we placed a load midway between panel points along this bottom chord, we would be placing this bottom chord into bending, which it likely was not designed for. The top chord, however, as I mentioned earlier, will often be designed for some bending, since it will likely support a floor or a roof, which will have some uniform load across it, such as people walking around, or snow load, or the weight of the floor or roofing materials. Now let's dive deeper into the behavior of these trusses. We have already established that the top chord will be in compression, and the bottom chord will be in tension when we have a simply supported truss with loads applied vertically. But what about the interior pieces? Can we detect whether these pieces will be in tension or compression? Well, let's start with the vertical pieces. These pieces have two primary roles. One is for stability. They provide extra bracing to the top and bottom chords. Second, they provide more panel points for loading to be placed. For example, if we apply a load here, say we are hanging a large heavy banner in an arena, that load cannot go into the bottom chord directly, as we learned earlier. There are also no diagonal pieces at this node for the load to go into. And so the entire force must go into the vertical piece. And since this force is pulling down on the node, that vertical piece will be in tension. Similarly, if we apply a load at a node up here, which also has no diagonal pieces immediately available at that node, but there are diagonal pieces directly below, the entire force will travel through this vertical piece down to this node here. And since the load is pushing down on this member, it will be in compression, like a column. So when we have vertical pieces at a node with no diagonals at one end and diagonals at the other, it's very easy to tell whether they will be in compression or tension. However, if we have a situation like we had up above, where we have a vertical piece with diagonals framed into the nodes at either end, that gets a bit more tricky. And in this case, we actually need to know what the forces in these diagonal members are before we can state what the force in this vertical piece will be. So we cannot clearly state yet whether this vertical piece will be in compression, as we drew, or in tension, without knowing what the forces in these two diagonal pieces are. So let's return to our truss and see if there are any other forces we can easily predict without detailed analysis. Now what if we place a load at a node that has a vertical piece framing into it as well as diagonals? Will any of this force go into the vertical piece? Well, there are no diagonals at the node below, and so there is no path for the load to continue if it were to travel down this vertical piece. And so no, none of the load will go into this vertical piece. And it will be a zero force member. And lastly, if you see a vertical piece with no loads applied to it at all from either end, it will again be a zero force member. And let's place one last load here at this joint. Which type of force will be in this vertical member? It will be in compression, like a column. Now, what about the diagonal pieces? This can seem difficult at first, and you might think we need to resort to some math to figure out which ones are in compression and which ones are in tension, but actually we don't. As long as the forces applied are all vertical downward forces, and we have a simply supported truss with a pin at one end and a roller at the other, we can figure out the behavior of these diagonals very easily with a simple trick. If we think about the deflection of this truss, its deflected shape will look something like this, where its maximum deflection occurs somewhere around mid-span. It may not actually be at mid-span because we have unequal loading here, but for now we'll simplify and say it happens somewhere around mid-span. So mid-span is where we have our change in curvature, where it is going downward to back upward. And so we draw a line cutting the truss at that point. Now if we look at each diagonal and its relationship to the deflected shape, if the slope of the diagonal follows the slope of the deflected shape, that diagonal piece will be in tension. If the slope of the diagonal is against the slope of the deflected shape, that diagonal will be in compression. So let's move from left to right here. This first diagonal follows the slope of the deflected shape, and so it will be in tension. The next diagonal goes against the slope of the deflected shape, and so it will be in compression. The next one follows the slope, so it is in tension. This next diagonal also follows the slope of the deflected shape on the other side of our change in curvature, and so it is also in tension. The next one is against the slope, so it's in compression. And lastly, tension. And finally, let's recall that the top chord is in compression and the bottom chord is in tension. Now let's take a look at our analysis software to see how we did. You can see I have the exact same configuration and loading, a pin at one end and a roller at the other. And now if we turn on our axial forces, you can see that we were exactly correct. And just to prove to you that this is a true truss, if I turn on my moment diagram, you can see there is no moment in any of these members. And also, if I turn on my shear diagram, there is no shear in any of these members either. We are only resisting these perpendicular forces through internal axial forces. In the next video, we will be diving deeper into how to analyze trusses, and there are two tools that we have for doing so, the method of joints and the method of sections.